Hello everyone. This is part 2 of topic 1 for exam 2, theory of the inverse functions and inverse trigonometric functions. We left off last time talking about a function being one-to-one. Here was the fancy definition, and we concluded that from that definition a function is one-to-one if a horizontal line passes through its graph in at most one point. So that was what we call the horizontal line test. So we saw how you can have, by the vertical line test, a function, and then by the horizontal line test, a function that's one-to-one. And so in this example, we had their theorem that said if a function is one-to-one, then it will have an inverse. So here's an example showing the one-to-one function f, and therefore its inverse, a reflection in the line y equaling x. I guess I could have labeled that as well here. So then the fact was that as they are defined, none of the 6 trig functions actually have an inverse, because none of them pass the horizontal line test. They're all cyclic or cyclic, however you want to say that word. And since they repeat themselves, horizontal lines, as you can see, hit them in an infinite number of points, okay, no matter what trig function we're talking about. So in order to define the inverse trig functions, what we do is we restrict the domain, and if we restrict the domain so that the trig function is one-to-one, by our theorem, it will then have an inverse. So we'll start with the simplest example, which is the sine function. You're not going to really be required to graph or anything, but this is important to experience this and to see what the graphs look like. But regarding the sine function, okay, I drew the grid and I scaled it off carefully, because in order to show the characteristics, to be able to show the inverse sine function being a reflection in the line y equaling x, we have to be precise. First off, for the sine function, it starts at 0, so there's the point at the origin, and at pi over 2 it reaches its high point. Pi over 2 is approximately 1.57, half of 3.14, and so that's where it reaches its high point of 1. And then it comes back down to 0 at pi, so a little bit more than 3.14 is pi, and it comes back down to 0. And then it goes on in that direction, as you know about, but that's all we're going to be concerned about here. Then in the opposite direction, negative pi over 2, which is a little more than negative 1/2, it reaches its low point of negative 1. And then at negative pi, a little more than negative 3, it goes back to 0. Okay, so then if we sketch this, sketching the sine function, well, it's just a rough sketch, but that's that piece, and then we've got this piece here. So that's roughly what the sine function looks like in that range. Now, what we do is we restrict the domain. So if I, let's say, shade in this portion until I reach the high point, that's as far as I can go, because if I go any further, it would no longer be one-to-one. But then to cover the complete range, I go in the opposite direction, and I pick up as much of the function as I can, and I'd have to stop at the low point, because if I go any further, it would no longer be one-to-one. So if we restrict the domain to negative pi over 2 to pi over 2, then it is 1 to 1, and we could define the inverse. Now the inverse is a reflection in the line y equaling x. So let's draw that. Passes through the point 1, 1, negative 1, negative 1, 0, 0. So the line y equaling x looks like that. And then using our spatial senses, remember what happens is the x's and y's are interchanged. So this point pi over 2 and 1 becomes the point 1 and pi over 2. So maybe roughly right there. And the point negative pi over 2 and negative 1 becomes the point negative 1 and negative pi over 2, so roughly here. And then if you reflect, okay, in the line y equaling x, that's the graph of the inverse sine. So what's in red there. So to sketch it out, so that's how we generate it. And just to make a rough sketch of it, what happens is we interchange the x-axis and the y-axis. So x, the domain now goes from negative 1 to 1. And the range goes from pi over 2 to negative pi over 2. And you can see kind of transposing what we've drawn there. This would be the rough sketch for the inverse sine function. So that's y equals, remember the notation, we use the superscript of negative 1, and so we read that as the inverse sine, or sine inverse of x. So that's what the graph of the inverse sine looks like. And so we define it. So y is the inverse sine of x. If and only if, you could say that the sine of y equals x. And this is where the domain of the inverse sine would be between negative 1 and 1, and the range negative pi over 2 to pi over 2. And we do have consequence of being inverses. We have the inverse properties, just like we had with E and ln. Sine basically undoes the inverse sine, so the sine of the inverse sine of x is equal to x, and vice versa. The inverse sine undoes the sine function, so the inverse sine of the sine of x is also equal to x. Remember, there's no cancellations here. These are consequences of them being defined to be inverses of each other. And there's different notations for the inverse sine. We're going to use a superscript of negative 1. So again, make sure you realize it does not mean a negative exponent. It means it's notationally indicating the inverse of the sine function. So the inverse sine of x, or sine inverse of x, but inverse sine of x is typically the way it's read. But you will see other notations. Another common notation is arc sine. So the arc indicating the inverse, arc sine of x. Or you could literally see it spelled INV sine of x. And obviously means inverse sine of x. And so everything that we did for the sine function, as I noted here, can be done for all the 6 trig functions. And there is a little handout that's titled Inverse Trig Functions, Inverse Trig Definitions, located in the Exam 2 Homework and Handouts folder. And this is what that document looks like. So it has the function, the inverse function, the definition, its standard trigonometric counterpart, and then the corresponding domains and ranges. Now, we will need these ranges, but I'm not going to force you to memorize them. So when you do the homework, feel free to use this, and when we have an exam and you need a particular range, I will supply them to you. And so if we went through the process like we did for the sine function, forcing it to be 1-to-1 and defining its inverse, those are the definitions we get. And here's a couple examples. We want to be able to do these without a calculator. Okay, find exact values. So the first thing we're going to do is start with the definition. Just realize that an inverse trigonometric function of a number is an angle. Okay, so this y is the angle, such that the cosine of the angle is equal to this value. So we change immediately by definition. So just like we had y is the inverse sine of x up here, and we wrote if and only if the sine of y is x, if y is the inverse cosine of this number, just like it says on our handout, if y is the inverse cosine of x, cosine of y equals x. So by definition, we immediately write that cosine of y is equal to negative radical 3 over 2. Now at this point we have to do some trigonometry, and we haven't really done trig together, so I'm just going to lead you through this, and you could do the trig any way you like, but here's what I do. The first thing is I identify the quadrants that the angle can be in based on the sine, S-I-G-N, of the trigonometric function of the angle. And that's using this little gimmick that you may or may not have seen, where we draw the Cartesian system and we say, starting in the first quadrants, you could say little phrase here, all students, and you go counterclockwise, all students take calculus. Okay, now you can use any phrase you want, but that's the one we typically will use. And this tells you where the trig functions are positive. All the trig functions are positive in the first, and that's by definition. The sine and its reciprocal cosecant are positive in the second. Everywhere else they're negative, except the first quadrant, because everything's positive there. Tangent, its reciprocal cotangent, are positive in the third, and so therefore they're negative in the second and the fourth. And cosine and its reciprocal secant are positive in the fourth, therefore they're negative in the second and the third. So that's the first thing you'd want to do, is determine what possible quadrants can you be in. And so since the cosine of this angle is a negative number, that means we can be in quadrants 2 or 3, because cosine is positive in the first and fourth. So what we do is we draw in the Cartesian system, draw angles, one in quadrant 2 and one in quadrant 3. But then, based on the range of the inverse cosine of x, you will be able to eliminate one of these angles. So again, you don't have to memorize the ranges. If we look at that handout, for cosine of x, it's between 0, the range is 0 to pi for inverse cosine. So the range of the inverse cosine of x is from 0 to pi. Now you have to think of this as an interval. And in the Cartesian system, we have 0 radians is the positive x, pi over 2 the positive y, pi the negative x, 3 pi over 2 the negative y, and then back to 0 or 2 pi. And so as an interval from 0 to pi would include 0, and we go as an interval to pi. So that means quadrants 1 and quadrant 2. So then we put the two pieces of information together. The fact that the cosine of the angle being negative told us we could be in 2 or 3, but the range of the inverse cosine restricts us to 1 and 2. Therefore, we can eliminate the angle in quadrant 3. And we just work off the angle in quadrant 2. Pick a point on the terminal side. Drop a perpendicular always to the x-axis to create your reference triangle. That's the right triangle. This is the actual angle y. But we use the angle that the terminal side makes with the x-axis as our reference angle. I like to call it alpha. Okay, that's a little alpha symbol. And based on the definition of cosine, which is adjacent over hypotenuse, so you have to remember the 6 definitions of the trig functions. I usually use, I'm going to get a separate piece of paper for this. I usually say Oscar had a heap of apples, some corn too, and that gives the sine of the angle, the cosine of the angle, and the tangent of the angle in terms of its opposites, adjacents, and hypotenuse. So that's what the O, A, and H stand for. And then you can get the reciprocals. Reciprocal of sine is cosecant of the angle theta. Reciprocal of cosine is secant. And reciprocal of tangent is cotangent. And by reciprocal, just flip them over. So those are the 6 basic definitions. I use Oscar. Some people use the following. Some people say some old horse caught another horse taking oats away. That one's kind of archaic. I don't think many people use those nowadays. But the one they'd use that follows this pattern is about the great Native American mathematician who used to be inspired. This is an urban legend, I believe. Used to be inspired to prove his theorems by going to a local stream and soaking his big toe in the stream. Hence they called him Sohcahtoa. And that gives it to you. Sine is opposites over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. So use your memory tricks, but make sure you know the definitions of the 6 trig functions in terms of their sides. Okay, so cosine is adjacent over hypotenuse. That means with respect to alpha, the adjacent is negative radical 3 and the hypotenuse is 2. And then immediately that should ring a bell because we have our 2 special triangles that you need to remember. There is the 30, 60, 90 right triangle, where the hypotenuse is 2, opposite 30 is 1, opposite 60 is radical 3. And then there's the other one, 45, 45, 90, where both legs are 1 and the hypotenuse is the square root of 2. So you need to know those as well. And so in this case, we're dealing with the 30, 60, 90. Opposite of alpha is 1. So that means alpha the reference angle must be 30 degrees. So the angle Y is 30 degrees, but the angle Y, I should say, is not 30 degrees because it's in quadrant 2. So the angle Y is going to be 180 degrees minus 30 degrees, or 150 degrees. Because to get the actual angle measure, you go all the way to 180 and then cut back 30 degrees. And the only thing about this is that you have to give your final answer in terms of radians. And if you want to use the unit conversion factor, multiply by pi over 180, 30 goes into 150 5 times, so 5 pi over 30 goes into 186, so 5 pi over 6. Okay, so that's the routine that I usually use. Use any routine you want. Let's do this next one to finish off this topic. And we have the inverse tangent of -1. So remember, the inverse tangent of a number is an angle. And you have to change over to you can't work with an inverse trig function directly. You have to change over immediately to its standard trigonometric counterpart. And if y is the inverse tangent of -1, by definition, again on that little worksheet, right? We could say the tangent of y is x. So if y is inverse tangent of x, tangent of y is x. Just basic definition, changing over to its standard trigonometric equivalent. So by definition, tangent of y is -1. Okay, now I'm going to express that as a ratio of -1 over 1. Okay, so it's got to be a fraction. First, we'll decide what quadrants are we in. Okay, so we already went over this concept up here that where the trig functions are positive. Okay, if the tangent of the angle is a negative number, tangent's positive in the first and the third, so negative in the second and the fourth. So I draw two terminal sides, one in quadrant 2. You don't have to be accurate to scale or anything, it's just, and one in quadrant 4, it's just a sketch. But then based on the range of the inverse tangent, you'll be able to eliminate one of these angles. And again, you don't have to memorize the ranges, but the range of the inverse tangent was -pi over 2 to pi over 2, non-inclusive, because of those vertical asymptotes on the tangent function. So it's -pi over 2 to pi over 2. But as an interval, -pi over 2 is actually, so this is what we went over before, -pi over 2 is actually the same as 3 pi over 2. So -pi over 2 to pi over 2, although they're non-inclusive at those endpoints, -pi over 2 to pi over 2 is quadrants 1 and 4. Well, some people will say 4 and 1, because it kind of goes in that order. But now we put the two pieces of information together. The fact that the tangent of the angle was negative told us we could be in 2 or 4, but based on the range of the inverse tangent, it restricts us to 1 or 4. Therefore, we can eliminate the angle in quadrant 2 and work off the angle in quadrant 4. So we pick a point on the terminal side, drop a perpendicular, always to the x-axis. That creates our reference triangle. This is actually the angle y, if we measure it clockwise, which would be negative. And that's appropriate because we want to be in the range of the inverse tangent. So then by definition, tangent is opposite over adjacent. And with respect to the angle y, the reference angle, there's the reference angle theorem. I neglected to mention that last time. But the reference angles have the same trigonometric value of the actual angle. And so tangent is opposite, -1, adjacent 1, immediately, that's your 45, 45, 90, because both legs are 1s. So we know that's radical 2, and the angle y must be 45 degrees. So therefore, y is 45 degrees, but you want to give that in terms of radians. So either memorize the conversions, that 45 is pi over 4, or multiply by the conversion factor, pi over 180. 45 goes into 45 one time, and 45 goes into 80, 180 that is, 4 times. So we get pi over 4. Alright, so we're going to be doing this not every day, but there will be a situation when we evaluate definite integrals that will require us to know how to find the inverse trigonometric functions of numbers, which again are angles. Okay. Alright, so that's the end of topic 1, and we'll see you for topic 2 when you're ready.